Je pense que c'est juste le son, mais n'est pas un mi pour le moment.
Yes, yes, I hear you. Thank you. Does everybody hear me well? Okay. So I'll briefly switch to French for the audience. Donc bonjour à tous. Nous avons le plaisir d'être réunis aujourd'hui pour écouter la synthèse du travail de thèse de Slimane Mzerguat. Et donc je voudrais simplement vous présenter brièvement le jury, donc qui est constitué tout d'abord de deux rapporteurs. Donc tout d'abord Louise Ara, qui est professeur à l'ETH à Zurich, et Étienne Parra, donc, qui est chargé de recherche au laboratoire franco-espagnol des Canaries. Les deux rapporteurs pour la thèse de Slimane. Ensuite, nous avons Alessandra Giunta, qui est maître de conférence à l'université de Catane, et David Brooks, qui est lui professeur à l'université George Mason. euh, euh, alors, j'imagine aux États-Unis, mais voilà. Et donc, les encadrants sont Éric Buclin, directeur de recherche ici à l'IAS, et Mio Janvier, astronome adjoint aussi à l'IAS. Et donc, j'ai le plaisir de présider le jury, Laurent Verstraete, professeur à l'Université Paris-Saclay, et mes excuses pour la présence à distance imposée par une fuite en vélo. Donc, je vais laisser la parole à Slimane, qui, j'imagine, va nous expliquer tout ce qui se trouve sur le superbe fond d'écran, enfin, en tout cas, celui que j'ai sous les yeux, du Soleil, donc nous parler des éruptions solaires et de tout ce qu'on peut en déduire avec les observations solaires orbiteurs. Slimane, c'est à toi.
For the study of the solar system itself, its origin and its evolution over time, also to study, to use it as a standard to measure the composition of other stellar objects and other like exoplanets or other objects as the stars or the exoplanets. And also, and this is what I'm going to do, it is an indicator of the processes that shape the composition and cause the variation. We are going to go into the photosphere as the easiest one to characterize, and then which is also going to be our reference for the composition for later. This is one of the latest data that we have about the composition of the sun. We have the logarithmic abundance as function of the number, the atomic number. And as usual, we see hydrogen makes the most of it, as it is also the most abundant. And then there is the helium, which is not only that the helium is the most abundant element in the universe, but also it is the ash of the nuclear reactions inside the sun. And the rest of the elements are the fingerprints of the stellar objects before the sun. And in general, the solar photosphere, we can consider it as a homogeneous composition. There is not a large variation except for orders of life cycle or solar cycles or the entire age of the sun. And we know that the sun, the photosphere of the corona is not, or the corona, or the plasma corona is, the plasma of the corona comes from the photosphere. However, the plasma of the corona does not have the same composition as the photosphere. There is a strong variation of the composition over the corona compared to the photosphere. And before we continue, we are going to introduce some parameters or some quantities that we are going to use throughout this work. First of all, we are going to introduce the elemental abundance ratio to the photosphere, which is the ratio of the abundance or the density of the element in a given environment, such as the corona and the solar wind, compared to the photosphere. And also, this parameter will allow us to see the variation of these abundance in those environments compared to our reference, which is the photosphere. So whenever it is equal to 1, that means we have the same composition as in the photosphere. And also we can take the ratio between two elements and compare them also to the photosphere, and that gives us the X to Y relative abundance ratio. And in this case, we are seeing the variation of one compared to the other. Why we are introducing this, it is in order to explain what is happening in the corona that causes the change. So basically, it is what we call the first ionization potential effect, which is, or in abbreviation, the FIP effect. And the FIP effect is, or the FIP is the energy that is needed in order to ionize the first electron of a given atom. And here we can see that this effect causes the elements with FIP value less than 10 electron volts to be 2 times or 3 times more fractionated or more abundant in the corona than in the photosphere. Here you are seeing the relative abundance ratio. However, the ones that above 10, they stay relatively around the photospheric composition. This effect is time dependent. It is between like orders of minutes to hours and days, which is so short compared to the large scales. Maybe we can see some small variations in the photosphere. So it is purely happening between the photosphere and the corona. And also here you are seeing different populations of solar wind. We are seeing solar energetic particles, which comes from the most active region, the active areas of the sun, which are the active regions. We are seeing also the slow solar wind. Both of those have a higher fractionation of FIP, and they are also coming from the boundaries of between the active regions and open lines. We also see the fast solar wind, where there is less fractionation, which comes from the least active areas of the sun, which is the coronal hole. And here, generally in remote sensing observations, when we study the composition, we have access to the ratios between abundances, the ratios between elements. So generally, we are going to use our X to Y. However, if the reference element here Y is a high FIP element, that means it will not fractionate, it is always equal to 1, this ratio and the abundance ratio would be the same. And from now on, we are going to call it either the fractionation value or the ratio between two elements or the FIP bias simply. And you can see here there are mainly 3 populations maybe of elements. So there are the low FIP elements like iron and silicon, there is the high FIP elements, and there is the boundary elements here, which are the intermediate FIP elements, or we call it here mid-FIP elements. So here you can see sulfur or carbon or phosphorus, for instance. And this goes to the objectives of our study. First of all, our goal is to try to get the remote sensing measurements of the sulfur and its composition in the corona. The second thing is to analyze the spatial and its spatial and temporal evolution over multiple studies for this composition. The third thing is to understand what is the physical mechanisms for the intermediate fifth elements that cause this fractionation. Okay. In order to do that, we are going to use data from multiple, or before that, we are going to understand, first of all, what is the physical mechanism that we have. So for now, there are multiple models that explain the Fib effect. However, one of the most successful ones is the ponderomotive force model. So we are going to give a basic explanation of this event and give an illustration of this. So let's consider that we have the two main populations of elements. So we have low Fib elements and high Fib elements in a chromospheric plasma. So here in the bottom of the chromosphere, we have low temperature and then low ionization on the elements. And then as they are evaporate, there is a partial ionization of those elements. And since there is, and that moment, we have a force that is coming from the gradient of the density of alpha waves in this environment. So here you are seeing the electric or the amplitude, the electric field up to 2 as under the derivative of the altitude. And since we have low Fib elements are easier fractionated, we are expecting at this altitudes to have more fractionation of low Fib elements because they are more ionized. And once it is going up to the corona, we have this fractionation or separation between those elements. And then we reach the corona where the entire plasma is ionized. Here, in the top of, or in the corona, all the elements are ionized, so there is no ponderomotive force that fractionates. In the bottom part, we have a weakly ionized plasma, so there is a lot of ion to neutral coupling that prevents this ponderomotive force to act. However, we have a sweet spot between the 20th to 20,000s of kelvins where the ponderomotive acts more efficiently, and this explains the 10 electron volts. Now, in order to study that, we need to describe the instruments that we are going to work with. First of all, we have Solar Orbiter, a mission that is sent in 2020 with the goal to study the solar environment, and entered its nominal missions at the end of 2021. It reaches a close approach of about 60 solar radii and also goes out of the ecliptic, so it can observe the solar caps. Right now it is at 17 degrees and goes up to 33 degrees. On this solar orbiter, on this mission, we are going to focus on SPICE, which is a spectral imager that observes the sun in temperatures between the upper chromosphere and the lower corona. And this is our main instrument to conduct composition and our main instrument in the thesis. And the third thing is the support instrument that we are going to use. In the point of view of Solar Orbiter, we are going to focus on supporting our study with FSI images, which is a full field of view broadband imager that observes the sun in two main bands, the 174 for the coronal structures and 304 for the transition region structures. And on the other hand, on the other side, we are going also to need the HRT for the magnetic or the photosphere magnetic field and for further extrapolation. Also, we are going to use Earth assets, and from this side, we are going to use the equivalent of SPICE in hotter temperatures, which is ice, and would be assisted with the broadband imagers like AIA and magnetograms like the spectropolarimeters like HMI. Now, once we get our data, we need first to do some analysis. So we need to create a tool for this. And this comes for this next part where we are going to describe my tool. So basically, the reason we need for this is the fact that at the beginning of my PhD, we still do not have that much tools for or dedicated for SPICE and data analysis. And also, the SPICE in itself as spectral imager needs a bit further complex analysis in order to have science-ready data. And also, SPICE in itself has its own challenges, where namely we have the point spread function of it is a little bit large, so we have to be careful and develop tools taking into account these kind of effects and other challenges. And this is the reason why we have dedicated a tool for that. And the SPICE data, if we are going to describe the structure, is mainly a set of multiple exposures at different expositions. And in each position, we have a detector image as a wavelength and the y direction. This would give us an intensity value for 3-dimension values, so the spatial dimensions and the spectral dimensions. And this instrument is a normal field of view, so we will need some co-alignment. And the spectral intervals that we need are specified by the solar orbiter observing plane coordinators. Now we are going to work with the L2 data, which have already undergone some the calibration and some preliminary data cleaning, like dark subtractions, etc. And now it comes the spectral analysis, fitting framework, and reduction of noise, or SAFRA, which is my tool in order to do the diagnostics and get the results science ready. Basically, this is the simplest diagram of the tool. It starts with data preparation. We are going to apply denoising or despiking and convolution. And all of those steps are user-defined, and it can be optional and also changeable. From all of those, we have error propagated from the data. So we consider those processing data when we compute our errors, except for the denoising. For the initial parameters, we have auto-loaded them from a catalog, which is also adjustable by the user. And now we come to the fitting part. In our study, we are using a multi-Gaussian model with a constant background, which is which could be also changed by the user. And the Gaussians, the number of Gaussians depend also on the lines that we are going to consider. The fitting weights are the errors that we have computed from the previous steps, and the output would be also calculated from those errors, and we have the errors for on each parameters. So up to now, we have tried to take this tool and test it against real data. And we have focused on an eruption that have happened in April 2nd in 2022, when we have a filament that have erupted between two active regions. And it was at 1 p.m. in the 2nd of April. 1 hour later, we have a flare that have been observed. And also, this work, or what I'm going to describe, is just a small part of the big spectral work and the big work in itself, with multiple instruments that are included, and there was a second author on that. Before describing the results, we have to give a little bit of layout on what is the eruption, so or solar eruptions or filament eruptions. So a filament eruption happens as a consequence of magnetic energy transferring into kinetic energy via reconnection. And here you are seeing the overlaying arcade as the flux rope is raising up. And then we have a reconnection where there is particles that are accelerated upward above this reconnection area and accelerated downward, compared to the reconnection area. And once these particles reach the atmosphere, they increase the intensity, and we can see the flare ribbons as a consequence of that. And sometimes even flares that follow after those eruptions or accompany those eruptions. These are the results of SPICE. Here you are seeing a tiny slot of the eruption. So here before the eruption, during the eruption, and here is the flare, or the flaring after the flaring time. And here we are also ordering them from temperature. So Lyman beta carbon 3, which are low top chromosphere transition region, and the top chromosphere, and then we have transition region lines, which is oxygen 6 and neon 8. First of all, we can see the primary flare ribbons of these eruptions in all the maps as a consequence of the heating that happens. And then we can see also the flare ejection that happens at the moment of the eruption. Also, we can see the hard X-rays whenever we superimpose the STIX observations on top of the spice, which are located at the flare ribbons foot points. And also we can see the new loops that have been formed. So we have a form of dynamics that happens during the eruption. And finally, we have the post-flare heating, where the hot lines like neon 8 starts to fill up with the hot plasma. Now, the Doppler maps show also this effect. The first thing we can see the red shifting in the primary flare ribbon area, and also we can see the eruption, the ejection part, where we have a plasma that is around 200 kilometers that is ejected from this area. And this observation also was confirmed by another observations from ice, of course, from another point of view, and we have also the same velocities. Now, we spoke about the PSF before, so we have to make sure that these are not artifacts. Basically, if we explain the PSF of spice, if we consider this a synthetic point in the detector, the PSF will broaden up the line, broaden up the image, and also it is tilted. So whenever we look into a given point, so at the center we have the Gaussians, and then as we go up and down we have some artifacts, so we can see them in here. However, when we go to the eruption area, we do not have any artifacts that are observed. That means we are safe to consider a real Doppler value. So as a given summary for this part and its application, we have developed a tool that created or analyzed the spice data. We have conducted a first spectroscopic observation from 2 points of view using ice, and also we have analyzed, even though I didn't mention it, we have had also an analysis of the flare, the flare portion of this eruption with extremely hot lines. And finally, since we have validated this tool with the dynamics, we are ready to go for the composition analysis with it. And this is the next part that we are going to study, to discuss. So here we are going to target some plumes using solar orbiter spice and study the sulfur composition. Before that, we have to explain what is a plume. So a plume is an elongated, bright structures that are extending upward in open field lines inside the coronal holes. So you can see here a sample coronal hole, and then in blue you can see the positions of those plumes. So the areas in between we call them interplume, which are generally the coronal holes that we have. And those elongated structures can be even seen up to 30 solar radii, which is an interesting structure because it contributes to the solar wind, and still there is discussions about how does those plumes contribute to the solar wind and its composition. Now, in order to study our interest is mainly on sulfur. So here we have the sulfur as a mid-field element, and as I said before, its fractionation depends on the environment. And also, spice in on itself gives us this opportunity as we can do sulfur diagnostics with this instrument. How we are going to do that is using one of the methods that are dedicated for the composition, which is the linear combination ratio. And before explaining this method, we have to understand what is or how we model the emission of the line. So in coronal composition, in coronal approximation, an emission of a given line is a function of the abundance of the element, which is the Fib bias multiplied by the photospheric composition. It is also a function of the contribution function, which is an element property that reflects the emissivity as function of temperature and density. And finally, it is a function of the DEM, or the differential emission measure, which reflects a environment property, which gives us the distribution of temperature and density along the line of sight. And in order to compute the composition, the LCR method bases on optimizing two sets of parameters from two sets of lines, one from low Fib and the other one from high Fib, and creating a linear combination between the intensities in order to find the Fib bias. And in order to find alpha I and beta I, the optimization parameters, we need to reduce this cost function. In order to explain this, we might have to look at it as an individual emission. So here we are modeling, or it is a kind of a modeling of the emission line using the photospheric abundance. And whenever we have this, we are expecting the ratio to be equal to 1. And whenever we have found alpha I and beta I that satisfies this condition, that means we have found the good parameters. And we do a sum over DEM, multiple reference DEM, in order to render our parameters DEM insensitive. However, it is still dependent on the density. For spice lines, the set of lines that we have chosen are sulfur lines and nitrogen lines. So here we have a true high Fib element as a reference to compare with sulfur. However, with the density, we have a slight issue. So for the data set that we have here, we do not have access to density. It is a little bit complicated to do. So once we compute the Fib bias and we take a mean for a sample map with different densities, we can see that there is a reduction of the Fib bias over time. So this gives us the idea. We compute the Fib bias using the highest density in a given coronal hole, and then we take the conservative values. Those conservative values as Fib bias. So whenever we have any fractionation, it is real because we have the least estimation of the Fib bias. And for the context, we have targeted a coronal hole, which is a part of a fast wind soup in 2024, in March 31st to April, where I have collected this soup. We have targeted two coronal holes, however, we focus only on one. So there is a small gap. So we have observed in one day, and then we start in another day, and then go back to this observation in another day. And then we have selected two plumes in those regions. So as I said, this is in the first set of observations. We are observing the plume, and the other one is not yet developed. And in the second one, we have no plume, and in the first one that have observed have decayed already, and the second area there is this plume that have already observed. So we will try to analyze those plumes before. So here we can see that we put the light curves of FSI as function of time. And you can see that the lifetime of this plume, or the plume one, is larger than plume two. So the first one is 6 days, and the other one is 1 day. The second important thing is that also the plume one is more intense and has a larger foot point than the one that we have seen afterward. The third thing is that since this one is long, spice was observing during its decay phase. So we observe in the first one during its decay phase, but and the second one we are observing it during its entire lifetime. These are the results of the Fib maps. We are putting here the Fib maps and the supporting radiance maps from spice. So this is a nitrogen 3 map, which is the same line that we have used. So the Fib maps corresponds to the same temperatures as nitrogen 3. We have also neon 8 and magnesium to see the transition region and the coronal structures. So you can see in the first one here, we are seeing the plumes, the plume one, and in the second set of observations, we are seeing the second plume. However, the first plume was observed only by spice during the first set, and then it was outside the field of view. And the first thing we can notice from the composition maps is that we have sulfur that behaves mostly as a high Fib element. It is something that is expected since we are inside the coronal hole. Neither mid Fib elements nor low Fib elements are supposed to behave extremely high as a high Fib, with high Fib bias. And the other thing, whenever we go down to the plumes, we see that there is clear fractionation that we observe in plume 1 during its existence, and the same thing could be said for plume 2. Moreover, for plume 2, before its observation, we can see no fractionation at all. That means that the Fib bias develops during the plume formation, and this is an important result from this. So now we have to understand whether the result that we have, the Fib bias that we have, is like above or below the error estimations. We have plotted here the errors as function of the Fib bias and scattered all the points that we have inside those boxes. We can see for sure, and of course, this green area is the area where the Fib bias is above 1 and also well above 1 beyond uncertainties. And you can see that plume 1 during its existence, there is clear fractionation even above errors. The same thing could be said for plume 2, and also before the existence of plume 2, we have no fractionation at all. We can also remind that this is done with highest density estimation. So those values that are well below 1, they are the consequence of the density assumption, and there is nothing of inverse Fib there. And now we try to understand whether there is a clear evolution over time. So here you are seeing the Fib bias or in the mean Fib bias in different plumes as function of time. And you can see, first of all, that the mean is always about 1.1, 1.2, and up to 1.3. And you can also see that in plume 2, before its existence, there is no fractionation, and then we start to see it. However, one might follow some variations here, but it is not possible because we have to remind that the density is not, we have fixed it while it might not be fixed. And now we have done the same analysis, taking the upper bound and the highest bound of the Fib bias estimation and use them as the error bars, and you can see that the error bars are large above the variations. So unfortunately, we cannot say anything. Still, there is an important discussion to be done from the result that we have before in the terms of why we have Fib bias or fractionation in coronal plumes. First of all, we have to understand the morphology. So this is an illustration that is adapted from Command 2022, explaining what is the components of a plume. So here, their explanation is that a plume is a set of small magnetic loops that are forming between the main polarity and the small polarities or the parasitic polarities within this main patch, and creates what we call plumelets. And by permanent or continuous reconnection, we have small jet events that they have called jetlets, and together they form the big structure that we see in the plumes. Why this is interesting? Because by continuous reconnections, we have a good presence of alpha waves. And comparing them with the model of Martin Lemming, which is the person who's the person that developed the model, in 2019 he predicted that sulfur and other mid-Fib elements could behave as low-Fib elements whenever we have chromosphere or we have alpha waves penetrate deeper into the chromosphere. And he gave different possibilities that we are going to compare with the plumes. So either by torsional alpha waves that leak deeper into the chromosphere, that are more appropriate for interchangeable connections and opens or large open structures, even with chromospheric connections where we have small, extremely small loops, which is something that we are expecting with the plumelets. And they have also spoke about the slow and fast mode conversion, even though lately there is a debate on whether the slow fast mode conversions are contributing sufficiently into the fractionation. So basically, we are going to consider one of those two. And in conclusion, as a summary, we have detected a good fractionation signature in the coronal plumes, which is one of the first ones for the sulfur in coronal plumes. We have localized it in the foot points, and it's clear that it appears and after the formation and disappears after into the photospheric composition that is expected for a coronal plume. Finally, we didn't see any clear variations during those lifetimes. And we have found consistency with the Ponderiomotive force model predictions of the sulfur behavior and other mid-FIP elements. And now, since we have spoke about the Alton waves and the activity, let's go beyond and try to understand the FIP bias, but in more active areas. And this is what we are going to do in this work. So the reason to do that is because the complex or the IRs have a complex magnetic topology and dynamic aspect. Also, in this study, we are interested in comparing what the mid-FIP elements fractionate compared to low-FIP elements. However, we have some challenges here. Before, we could have escaped the density issue, because in a coronal hole, the 10 out of 10 is the highest density that we get, and it is generally variating, but not that much, like it is at the beginning of the variation. However, in the active regions, we can have densities that go up to 11.5, which is right at the highest variation that we can get with the density. So our analysis is extremely density sensitive if we use our approach. So what we are going to do is to compute the FIP bias for both densities. And depending on the location of the active region, we can estimate which one are we in the upper bound of the density estimation or at the bottom part. The location that we are interested in is an active region that have been targeted during October 2022 for an IR long term, where we have observed an active region for 10 whole days. The Earth field of view entered by by the mid of the observation window of solar orbiter. That means we have observations with SDO AIA and Hino ice, which is important because we can have access to low FIP bias with this instrument. The area that we have targeted is a decade active region. However, we can subdivide it into three main areas. So we have the northwest with small loops, the central area where there is the core loops, and we have a fan loop area, which we call it the southwest region. And also we have a small flux emergence at the end of the observation. So all of those three are going to be analyzed as one in our FIP bias measurements. This is the result that we have got. As before, we have the nitrogen 4 lines, which is one of the line to do the FIP bias. So we are at the same temperature for the FIP bias as the nitrogen 4. We have the magnesium to identify the chromospheric, the coronal composition. And we have measured the FIP bias for two densities. So this is the lowest density that gives us the highest FIP estimation. And this is the highest density, which gives us the lowest FIP estimation. And we have added to that a mask for the areas where we have confirmed fractionation beyond errors. So this is for the lowest density estimation, and this is for the highest one. First of all, we notice in the fan loop area, it is the only area where we have good or possible fractionation of sulfur. And we are going to consider that the FIP bias, even though we are considering the lowest density, we still are at the lowest part. So we are at around 10 up to 10 or 10 up to 9, which is going to be close to this density. The same thing for the coronal loops. However, in both maps, we see no fractionation. So we are sure that sulfur behaves as a hyphae in the core loops. And this is also the same thing for the northwest area, where there is not sufficient signature of Fibb bias. Finally, the emerging flux that we have observed at the end have also no fractionation signature at all. Now we take these results and then we compare them with what we have done with ice. So with ice, we took the same approach, so the same method, and then we have applied it for silicon and iron lines compared to sulfur. So here sulfur is the reference, and the temperature is different between ice and spice, of course. Here we are at 1.52 million kelvins, so it is the mid-corona, and here it's still at 100,000, which is in the mid-transition region. And these are the results that we have found. This is quite interesting because in the closed loops, there is more fractionation, and it is clear that is within the foot points of those loops. And it is also seen in the core and in the northwest area. In the fan loop area, however, we have the inverse effect, where we have a lower fractionation of iron and silicon to sulfur. And also, we have in the emerging loop a strong fractionation that have been observed in there. And it is also correlated with the foot points of those emerging loops. Now we are going to discuss those results for spice and ice. So why in spice we have sulfur fractionates, or there is a signature of sulfur fractionation in the fan loops, and there is nothing in the core loops, while it is the opposite for ice. So going back to the model of Martin Lamming from a work that have been done before, the closed loops here, there is a correlation between, or he predicted that there is a correlation between the alpha wave resonance and non-resonance in terms of fractionation. So he found that resonant alpha waves have more capacity to fractionate the iron and silicon. However, for non-resonant waves, it can also fractionate the sulfur. And we have to mention that ice and spice are observing at different height. However, spice still is above the fractionation of 20,000 degrees. So we are expecting that the sulfur is the same at spice height and coronal height as a first approximation. So that means that iron and silicon here are not, or the measurements, the Fibb bias that we have are not only for iron and silicon, but also the contribution of sulfur into the fractionation. And in the flux emergence, we have also the same conclusion that we can get, that as the flux is emerging, the loops are closed and reconnecting, we have more resonant alpha waves that fractionate iron and silicon and do not act on sulfur. And this gives us the main implications of the study. So first of all, we have a fractionation that depends not only on the wave activity, and also on the magnetic geometry and the wave types. Also, the sulfur diagnostics is a good element in order to further understand the ponderomotive force. And also, the sulfur is a good element to analyze, as we see it fractionates in open structures, and this is a good thing for slow solar wind analysis and composition and linking with solar wind. And finally, this is an important note, is that generally in ice we use sulfur as a high Fibb element. However, we have to be careful. This is true in general. But whenever we go to smaller located areas, we have to take into account the fact that sulfur can also fractionate, and this is important also for solar C, that would be a high resolution spectral imager. So now we go to the conclusion. We have developed an instrument, Saffron, that is a robust pipeline that gives us the data or the information about the composition. We have applied it to do the first stereoscopic spectroscopic observations using ice and spice. We have remote sensing detection of sulfur in the coronal plumes. And also we find a fractionation of sulfur that is more in open-like structures. And this goes well with the predictions of the conjugative force model. However, this work is not yet ended. There is a lot to do next. The first thing that we are interested in is that the fact that we don't have any direct measurement of the waves. So generally we are basing on what we are used to have in those regions in order to conclude on the wave activity. But there is, for instance, a work from Rabitu in 2024 that tried to measure the alpha activity in the chromosphere and link it to the ice observations and the composition measurements. That would be great if we do it also with SPICE. Also, it is a closer in terms of height into the chromosphere. And the second thing is that although we have done a good analysis with SPICE doing the composition, still there is two main points that have to be addressed properly, which is the density diagnostics with SPICE and the opacity effect. So here we are at the transition region, but so that means we are start to flirt with the opacity problems. So we have to have a dedicated analysis in order to quantify these issues. And also, we have proven that the mid-FIP elements have their own physics to be explored, and there is a good work to be done in combination of the mid-FIP elements measurements with SPICE and low-FIP elements measurement with ICE, or even in Solar C, where we will have both of them, in order to combine the theoretical models and expand on them and go beyond the conjugative force model as a simplistic, like a model that gives predictions on the average chromosphere behavior. We have done a work in the plume in one region where we have observed two plumes and in one active region. However, we do not know whether it is a general case. So here, it is an important thing to have a generalized analysis in order to understand sulfur behavior. And you can see here an active region that I'm studying right now where there is a clear fractionation. So the difference is that this one is young, and there is another coronal hole that have been observed in 2025 where there is this open structure. So we can also see the fractionation. That means that what we have observed is not just a case, it starts to be a general rule for sulfur fractionation. And finally, unfortunately, it was planned to have a link-in with solar orbiter in-situ measurement of the composition. However, his was out of commission. That means for the future, we have also the chance to do this same study, but with trying to link with the composition in measured around the Earth, whether with wind or with ACE. And those two are the projects that I am working on right now. So the density characterization of the opacity issues and the generalized analysis on the active regions. In another note, or in a lighter note, these are my contributions that are beyond my PhD work. So I have contributed in the solar orbiter observing plan. So I have co-led the soup that I have spoken about. I have led my own soup, LTP-17, and I have also trained the next soup coordinator for the LTP-19. I have also contributed into SPICE community and the data improvement via reporting issues in the calibration telecom or proposing solutions and also presenting in the consortium SPICE. Also, there is multiple events and collaborations where I have presented my work. So for instance, this is the Lizouche Summer School. And finally, I have taught for 2 years the electricity, hydrodynamics, and meteorology, as well as I have been selected for the ESA archival research program for the last year. Adding to that, there is a paper that is close to submission, but not yet, on the sulfur fractionation, and there is a work in preparation on the active region. I have also co-authored a work during my first year of my PhD about the second vapor eruption, and I have also a small contribution as a co-author in a work by Yin Ji et al. Thank you for your attention, and if there is any questions.
Hello?
Yes.
Yeah, okay, I hear you again. So thank you, Slimane, for this lively and clear presentation. So we have now time for questions. So I turn to the first referee, Louise Ara, if you wish.
Of course. So, hi, Slimane. Can you hear me okay, first of all?
Yeah. Hi, Liz.
Hi. And many thanks for your presentation. It was very clear, and also for your thesis. There's a huge amount of work has gone into this, so thank you very much. So you did in your summary slide, you're describing where you want to go next, and you've described the punter-motive force idea multiple times in your thesis. And do you think that there are any weaknesses in the actual model, or do you think the issues are related to data?
I think that comes from both. The data have its limitation and the model have its limitation. So for the data, or maybe I would speak from the SPICE side, there is always an issue for maybe the PSF contribution, the line blending. So there is always like some possible problems that you would have as a contribution, and there is always instrumental issues that like reduce the estimation of the field bias. And from the model side, so the Martin, like the Lamming model, is quite interesting, but still it is a kind of general model, like static, considers a static chromosphere, and also does not like take the dynamic aspect of the chromosphere in a 3D dimension, etc. And there is also something, I think, a study from Victor Rivi, where they used a realistic turbulence model for the chromosphere. And from what I understood, they found that the ponderomotive force reproduces the result in the cases of in the cases where you have a given amplitude of the alpha waves, which is not something that we have in the chromosphere. In the chromosphere, we have a spectrum of alpha waves. So I would say that the limitations come from both the model and the instrumental side.
Okay, so on the model side, you're saying it's mostly because of the lack of dynamical input in the chromosphere, which we know the chromosphere is very dynamic.
Yeah.
So how do you think that would affect your results if the model was updated? This is a very hard question to answer. So do you see any inconsistencies between, you've kind of said your results are consistent with this model.
Yeah.
Do you see any inconsistencies that might suggest weaknesses in the model related to what you've just described? Or is it not at that level yet in terms of the data quality or?
Well, there is a part of this. I don't want to give harsh conclusions on that, like whether it is like 100% dependent. However, so maybe one of the things that I have noticed is that I have mentioned that in open-like structures, the sulfur is more fractionated. And my issue is that whenever I tried, so for instance, for these new projects where there is like a large amount of active regions, there are some areas that they are extremely active. So when you see in FSI, there is enough activity in those areas that you expect that there is a good spectrum of alpha waves in the chromosphere, on the top of the chromosphere to fractionate, and the areas are funnel loops, and you don't see anything. And the other hand, so for instance, for the active regions that I am observing, one of them, we have like a really small loop, but still we have sulfur fractionation. So this maybe is an indication that the openness of the magnetic field is just a second consequence, but it goes back to what Lamine maybe have given in as an explanation, is that whenever you have like deeper or more alpha waves that penetrate deeper into the chromosphere, we start to have sulfur. So maybe we have small loops, but we have intense activity that creates this chromospheric waves that fractionate sulfur. Yet this is only my input. I didn't do any modeling during my thesis or simulations during my thesis or modeling of the conjugative force, but it is only what I have observed from the data and tried to rationalize.
Yeah, but you've tested the model quite hard, haven't you? So, yeah. So one of the things you mentioned as well was you would like to quantify wave dynamics better. And of course, we see waves everywhere. How much better, and what would you use to do this, or what do you need to use to do this to be able to help understand?
Well, this is like not only a starting idea, but I might think as a first thing to do is to have the same work that Morabito 2024 maybe have done with ice. Sorry, I forget the ground-based instrument that they have used, but I know that they have used calcium-2 lines, which are chromospheric lines, and used the Stokes parameters in order to infer the velocity in the velocity field in the chromosphere, and then try to compare this by with the observations in the low in the observations of the corona of the Fib bias in the corona using ice. And the first thing, maybe, which is the straightforward thing to do, is to have both sulfur as a mid-Fib element and another low-Fib element with ice, and also sulfur is observed with spice, so we are in a much lower altitude than that of ice. So maybe we don't need even the extrapolations. And then try to find the locations where we have correlation and the locations where we do not have those correlation, and try to understand what makes these areas fractionate or not fractionate, like what is the other cases. And maybe this would steam out something about how to go beyond in terms of making the conjugative force more complex and includes more physics.
So you think that you have the instruments with the capability to do this, but the coordination has not quite been in the right place, right time?
Yes. I'm not an expert of ground-based observation, so I don't know. But from what I've heard, it is really hard to do compared to maybe solar orbiter, where it's, at least to my experience, coordinating with Hinode and Iris was pretty much easy. But yeah, I would say something along the line of the coordination. Yeah.
Okay. So in your the work related to the flare aspects, you did a lot of work with saffron and everything to build up to this.
Yep.
And you make a comment in your thesis to say that the spice and ice observations are fully consistent with the 3D flare model.
Oh, yeah.
So when you say fully consistent, is there any areas where you think that it's not fitting well, or you mentioned the flows were fully consistent? What kind of flows do you expect from a flare model you observed?
What do you mean by flow in this case? Like the eruption phase, or the flare, like the flow of plasma during the post-flare heating?
Yes.
Okay.
The latter.
For this one with spice, I would not draw conclusions on that, because during the post-flare heating, we can see Doppler shifts, but I would not trust them because the velocity is low. So basically, with SPICE, I'm pretty aware that you know that with SPICE at that moment, any Doppler velocities that is below maybe 80 kilometers per second, that's like at the state of the data, it is not trusted due to the PSF contribution, and also the PSF is higher whenever we have larger gradients of intensity. So the flare loops, that would be like highly intense. So we are expecting some like strong, crazy PSF effects there. So I would not do any comparisons in terms of the output of the flow, even though I would give you what I have seen. So in the flare area, we have seen some downflows, but they are in low intensity.
So can you explain when you said in your thesis the SPICE and ice data are fully consistent with the flare model, what you mean by that?
So what we have meant by this, or maybe it is about the formulation, is that the entire events from the eruption and flares, eruptions passing through the flares, and the measurements that we have in terms of intensity, the locations of the flare ribbons, and the locations of the hard X-rays emissions, and the post-flare heating that we have observed, as well as the reconfigurations, all of that align with what we have in the standard flare model, the 3D standard flare of model, the 3D standard flare model. Sorry.
That's okay. It's hard to
Yeah.
say. So what are you saying is consistent then from SPICE and ice? You say the intensities are consistent. What does the model expect from the intensities?
The intensities, by intensities I mean the structures that we have observed. So
okay.
At the beginning, we see the phase of the flux rope rising, and then we see the flare ribbons that have occurred or been observed after the eruption. And also maybe we can add the fact that we have observed or located the hard X-rays that are expected to be along the line of the concentrated areas within the flare ribbons, magnetically concentrated areas. And I would say this is pretty much, if I have not forgot anything else.
Okay, yeah. So it's mostly based around the morphology and locations of hard X-rays, etc., where you say it's consistent. Okay, so
at least this is what I said from the SPICE part. I'm pretty sure there is more stuff, maybe if we include other instruments.
Okay. Okay, so when again thinking about flares, to determine the trigger mechanism, what information do you think you need? So going back to that flare which covered all of the different phases, right? Is there anything in additional you think that you would need to observe to really understand the trigger mechanism, or do you think that was fully covered?
The trigger mechanism for the flares?
Yeah.
Well, I would say the magnetic topology. So with it, you can have you can have the extrapolation, and then you can have the evolution of the magnetic fields. From that, you can have an estimation on the trigger mechanism. And unless if I'm wrong with that, I'm open for correction. So
So what would you say triggered this flare then?
Oh, for this flare from the 2nd of April, it was like the first thing that we have observed that triggered the eruption was the appearance of new, or the emergence of new polarities below the filaments that have erupted eventually, and this have applied a pressure on magnetic pressure on the structures that have already existed, and then initiated the rising of the flare, eventually triggering this reconnection and the eruption itself.
Okay.
Mhm.
Thank you. So we go on to your plume work.
Yes.
You unfortunately didn't have any HISS observations during the time
It's
of
so
your
unfortunate.
observations, which is very, very sad for everybody. But if have you been able to do, or what would you expect the in-situ observations to show from previous observations in situ?
From previous observations.
Yeah. So
Okay.
not that you didn't have any at the same time, unfortunately. But
Yeah. So from previous work, in general, whenever we look into the plume, so we are looking into the coronal area, and we are expecting, like, as the instrument or the wind passes, or these different sections of this the area passes by underneath the instrument, we are expecting something like the photospheric composition of sulfur, and then there is an increase of sulfur composition, and then decrease again. So as we pass by those areas, and let's consider that if, in case we have a robust remote sensing observation of sulfur, let's consider that we have multiple plumes, we can pinpoint the locations, at least that whether we are within those plumes or outside, or which plume, if we have like a high fractionation of plume at a certain a position than other one. So we can pinpoint which plume we are in. And this is already a good way to go forward on terms of linking with the composition. So generally we compare sulfur to sulfur, or maybe even not sulfur. If we don't have sulfur observations with in-situ measurements, we can use other intermediate elements. However, we have to make sure first that those elements are as predicted by Martin's model to behave like sulfur as intermediate elements. In a nutshell, this is what I would expect, and this is also what is in the data. So in the fast wind, most of the time we have photospheric composition, and then sometimes we have fluctuations of sulfur. Can I add something also?
of course.
There is a study in 2016 that I think I don't remember the author, where they studied the dynamics, simulated the dynamics of the plumes, and they found that there is some instability in the wind that could be created and mix the plasma. So all of this that I am saying is what I expect, but still I'm expecting some mixing in the plasma, and then like we lose the location of the sulfur, like locating the sulfur in itself, and the composition will not be the same as what we observe in the corona.
That's why I always think it's a big challenge to connect those up. I was wondering what your opinion was, because do you think the switchbacks have got any impact on what the Fitt bias would look like in the solar wind? I have no idea myself, so it's a.
So are we expecting strong switchbacks from plumes? Isn't it like from jet structures, like jetting structures, or because in plumes, even if there is switchbacks, it will not be that powerful to cause enormous mixture. So
maybe not. I don't know.
Okay, I think Etienne Paria knows a lot about this, so
He can answer
I
my
would get
question.
certainly a question about
You
this.
can answer my question. Okay, so you've had some challenges with data, which there always is with data. So if you were to have your dream instrument that solved all these problems, have you got an idea what it would be?
What do you want
If
me
we give
to
you
search for?
whatever
What it
money
could
you
be?
want.
Sorry?
What would be your dream instrument that would avoid some of the challenges you had with the data?
Okay, so high sensitivity. So to have the fastest rastering possible, to have time variation and the highest resolution possible. But yeah, I told you this is my dream instrument. I don't think it would exist. Yeah, no.
It could eventually. Keep your
Yeah,
dreams.
no. In a more serious way, I think that the first thing maybe we are going to be interested in is an observation with small time intervals. I had a discussion with Giulio Del Zana like in my first year, and he told me that he had already observed like Fib bias changing in a matter of like 15, 30 minutes. So it is something pretty much important, because if we see those kind of dynamic variations of the composition, it is way easier to link to the dynamic aspect in the chromosphere. So we have the time interval. If we don't have a good time, like a good cadence, we can opt to high resolution. So we are observing a plume, but a plume is a large structure. It would be interesting if we can subdivide this plume, if we have like really high resolution or good resolution, in order to understand where exactly this fractionation happens. And this also would lead to understanding where the position, or like correlating with those alpha waves that are propagating into the chromosphere. And maybe, yeah, one of those would be already a dream instrument.
Okay. Okay.
Oh,
Thank
sorry.
you
And
very
another thing, a last
much.
thing, the ability also to observe multiple spectral lines. This is another important, because one of the issues that we have maybe with SPICE is the lack of density diagnostics, temperature, and also it would be great if we have correlated LCR with the DEM inversion method, but for that we need multiple lines to do a DEM inversion. And yeah, this would be great if we could have an instrument that gives us the Fib bias in multiple heights.
Okay. Okay. Thanks a lot.
Thank you.
Thank you, Louise.
Thank you.
So we can turn to Etienne.
Hi, Slimane. Thank you very much for your presentation and for
Thank
your
you.
thesis. Can you hear me?
Yes, I hear you.
Okay. Thank you very much for your document and for your thesis. I found it very easy to read, very deductive. It was really a pleasure to have it. Also very interesting, the results that you are starting to obtain. I think there is a large potential, and also congratulations for the development of Saffron. I think you're bringing a tool to the community that is going to be very extremely useful. I mean, you've been a bit cursed by the use of SPICE and your with the difficulty of analyzing data, and you're really helping in trying to get the most of actually a very interesting instrument full of physics. I have a couple of questions on your document. I would like to start with things that I've not fully understood. If you can go to your presentation slide 47, I think.
47. Oh, yeah. The
Yes.
method, explanation of the method?
Yes, this is about one slide back. This is about the choice of the alpha high and beta high on the linear combination method.
Yeah.
I mean, how do you proceed? How do you choose them? What do you do exactly?
Oh, so basically, we have this cost function, okay? And this cost function, we find the closest alpha I and beta I, so this is equal to 0. and the contribution function is already tabulated for each density. The DEM that we use are reference DEMs, so we sum over multiple DEMs, and the abundance are the photospheric abundance. I have shown them already in the beginning, which are relatively well measured. And now all what we have to find is alpha I and beta I. So we reduce this function, or we optimize this function to find alpha I and beta I. In general, this function is nothing but the same combination ratio. Instead of using our observed intensity, we simulate a intensity of this line if we have the abundance of the photosphere. And since, yeah.
When you're saying you simulate, I mean, what is being done? I mean, and you say you've done it, or I mean, how?
No. By we, I mean the method that does it. So this method is created by Natalia, and the choice of lines for ice and for spice have already been done like way before, and I just used them. So for the sulfur and the nitrogen lines are the best lines that have no temperature issues, because we cannot choose any lines. So these are the best lines that we have and gives the best result. So we use the contribution function, for instance, of nitrogen 765 and nitrogen 991, and those are already tabulated. The same thing for the photospheric abundance. The abundance of the nitrogen lines here will be the same, because they are the same lines, different transitions, that's all.
And so the tabulation, how is it done?
Yeah. And whenever you find alpha I and beta I, you plug them here, and then you put the real intensities. Because if the intensities are corresponding to the same intensity emitted by the by an element that is abundant, that has a photospheric abundance, the results would be 1, because alpha I and beta I are optimized for this one. However, if it is like over 1, this intensity corresponds to the abundance that, the abundance of the corona. That means it is the photospheric abundance times the Fib bias. So in this structure, in this formula, the Fib bias times the abundance in the photosphere will get out. And then you will have, instead of 1, like this, you will have something like Fib bias.
Mm-hmm. Okay.
I hope I am clear. If you are here, I could use the table to explain.
No. Well, anyways, and the tabulation, how is it done? You were saying that they have been tabulated. How has it been tabulated?
So, which for the abundance, it is work that have been done already. Whether they study using the visible spectral lines of the photosphere, but it is way more complicated than in the corona, because the corona we are in like an optically thin lines. So in the photosphere we need to do a kind of composition measurements, but taking into account the absorption effects and like taking into account multiple effects. So there is a modeling part on that, and the results are tabulated. For the contribution functions, there is a community that already calculates, do the atomic calculations. It is purely atomic of the emission on this of those transition lines under given density and a given temperature. Of course, considering maybe the exact transition in itself. And these contribution functions are evolving over time. So I will give you one of them. For instance, here, these are the contribution functions at a fixed density of around 10 up to 10 per centimeter cube. And I will give you an example. There is a Chianti. Chianti is a group that does also does this these calculations, and I use their database.
Still on the linear combination ratio method.
Yeah.
You're writing in your thesis that there is some assumption on the uniform fractionation. How is it done? I mean, which lines are known to be fine and which one are not? I mean, what is the...
uniform fractionation. Can you give me the entire aspects, because I'm thinking of two things. So maybe I would give you what I am thinking of.
So
as the
page
most probable.
25.
Yeah.
You write, it should be noted, however, that the assumption of a uniform fractionation among all low FIP or high FIP elements has not been universally verified. It must be assessed case by case, right? So how is it done?
Maybe you are referring to that whenever we use a set of spectral lines. So for instance, with ice, we have silicon and iron. Maybe we use them all together. Here you see that there is a summation between multiple transitions. So imagine that we have a transition of iron and a transition of silicon. So we are observing the abundance, the Fib bias of silicon and the Fib bias of iron, or maybe iron and the magnesium or something like this. And whenever we take out, we consider that all the elements fractionate the same. So the Fib bias that you get is a mean Fib bias between all the elements that are included in the transitions that you are considering. Here it is way easier because we only have sulfur. So the same element, the same fractionation. However, if we go, for instance, to ice, yes. If we go to ice, you can see here the lines that we are using. Well, as a low FIP element, we use sulfur, but as high FIP element, we use silicon and iron. Although in this case, it is pretty much the same if we consider that the ponderomotive force is the only contributor to this fractionation, because they have a close FIP value. You can see it maybe down here, like 7.9 and 8.1. But still, we have to be, this is something that has to be said for mathematical reasons, that this is not the Fib bias of a given element or a given element, but the mean on what it is giving us. Okay, am I clear on that?
Okay, yeah. Now, about saffron. I mean, in your thesis, you're saying that the binning is indeed changing the size of the data matrix. So basically, you're lowering the resolution. Yeah. But why is it a problem? I mean, are you not oversampling? I mean, what is the pixel size and the actual resolution size?
The pixel size and the this is okay. I would answer this on two main aspects. Okay, there is the first aspect is that I am in need of a matrix that does not change its size, because I wanted to use the coordinate systems that in order to reproject in a way that does not mess up the positions of the pixels. Because if I create the world coordinate systems, the reprojection class that I am working in, I risk to have shifts. And the second thing is that during my first, I didn't mention it here, but this is what I have done. During my first work on the eruption, I needed to get the highest possible resolutions, but sometimes the intensity is well beyond like the quality that we need. So I don't need to bend the entire matrix. So what I do a kind of convolution, and only the convolution will allow you to do this, that is adaptive. So it is like a refined mesh, but for the convolution. So I only convolute the areas where the signal is low, and leave the ones that are like good. So it means like without any convolution. Why I do this, it is because I needed at that time really good resolution possible for the eruption as it happens, so we can extract the most of information. In the same time, I don't want any artifacts in my observations. So the areas where it is dark, I don't want any artifact of whether Doppler shifts or intensities that are badly fitted. So what I have done, I did this convolution, and then I depend on the area on the map. You have some areas with high resolution and some areas with lower resolution. So this is the entire premise of the use of the convolution rather than the binning. And at the end, the information about the binning is included inside the convolution matrix. So I just can have a jumping selection of the matrix, and then I recover the binning. So at the end, I am winning in both ways.
Okay. Speaking about this adaptive convolution method, which is interesting, what are the typical parameter range that it is?
Sorry, can you repeat?
I mean, you're having this. I mean, you're outputting this convolution matrix. I mean, this convolution size, but how by how much does it goes? I mean, what is the minimum value and maximum value, which is generally being used in your data?
Maybe I didn't specify it in my thesis, but yeah, there is a minimum and a maximum value. I don't remember exactly for this project that I have done what is the minimum and the maximum, but I have chosen something along the line of the range of the PSF of SPICE. I think 10 pixels at max. So the basic work of it is like I do the fitting at the lowest resolution possible. I estimate the errors, and whenever I have a threshold of an error that is like higher, well, the errors that I have computed that are higher than this threshold, I refit again, but this time I start to include more and more pixels. So at least until it finds the good error that is below the error bars, the threshold, or it reaches the maximum at this case. So I don't not want to take the entire map to fit.
But what is the typical value for those, for the minimum and maximum?
For the minimum is 1. For the maximum, I think it was like around 10. Yeah, 10 pixels. So
10 pixels,
which would be equivalent to 10 arc second in y direction. Yeah.
Okay.
Mm-hmm.
Something what puzzled me, I think it's figure 2.3 of your PhD.
Yeah. So wait, I have to pull out my PhD thesis. Sorry.
Yes.
2.3. Okay.
Yeah, 2.3.
Mm-hmm.
So you see, if you're looking at pixel position 420, 131, I think it's one at the bottom row, second from the left.
The second from the left, the bottom, the third, 420.
Yeah, pixel position 420, 131.
Yes.
When you are applying the convolution, you see that for the wave at the wavelength around 703, there is actually a big difference between before and after.
Yeah, it is.
Which is something that you do not observe in most of the other signals. Do you understand what was happening there? I mean, why is there such an increase in this particular pixel?
Yeah. So what you are observing in those pixels, maybe should I share with everyone? Okay. So what you were observing that pixel is the raw spectrum versus the convoluted pixel.
Yes.
And here, when you see the raw pixels, if you are in a boundary region between high intensity and low intensity, of course you will have the contamination of the left or the right side. It's like binning. Like you may have inside a pixel that is low in intensity and other pixels that are high intensity, and whenever you bin together, you will have something larger or higher than what you have. So I think this is the only. And for the other pixels, it was just the fact that they were like within like areas with similar intensities that you don't have any difference.
Okay.
Yeah. So is this clear enough, or maybe?
Yeah. I mean, I have no clue about what's happening, but since you seem to understand it perfectly, that's fine.
Okay.
I was
So
surprised. No.
maybe you can
About
also look its location on the map, because the coordinate that I have put in the titles correspond to the location of the pixels. So you can see that it is in the area where there is like dark and intense patches. So maybe it is in the middle between them. So you have this not in the dark area next to a high intensity region.
okay.
Yeah.
About the spice astigmatism. You write page 62 of your thesis that K-limitation arises from the astigmatism in the instrumentation, which produce an asymmetry and spatially varying point spread function. Can you discuss a bit more about this? What is the level of the intensity of what's the impact of this astigmatism? What is the limit, and do you have any ideas of possible mitigation strategy that you've been applying?
Yeah. So this is the part of my presentation where I spoke about this. So maybe I would re-explain what I have done here. So this is a detector image. So we have the y direction and the lambda direction. Okay. And this is a point that I have artificially like enlarged just with a simple 2D Gaussian, and just to show the effect of the astigmatism. And when the PSF of spice is broad like this, when you like measure the or you get the spectrum in the middle here, you can get the Gaussian, which is something normal. However, like in the top parts, in the case of a perfect instrument, we should have nothing in there, but we have the effect of this white or this dots on the upper part. The problem is that it's not only a white PSF, it is only also a tilted PSF. So the intensity when it's wide in the y direction, it affects the wavelength direction in different places. So when you take the spectrum of this area, you see that you have another spectrum or an artificial spectrum, which is redshifted. That means it will give you a result that is redshifted. The same thing for the bottom part, which is blue shifted. And then when you go, for instance, in the map, so this is a map that have been done by Bill Thompson. Thanks to him, he tried to find the locations where there is this artificial Doppler maps. You can see when you go up and then you go down, you go from red shift and then to the green and then to the blue shift. So you are seeing that you have the same effect here. So as you are going from top to bottom, you see this effect, and it is also mentioned here. And this is the problem with the PSF of, or one of the problems that the PSF of spice causes. And the only way to do it is to try and model the instruments and like reverse it, like have a deconvolution algorithm. And the issue here is that maybe ask the spice people, we don't have the exact characteristic that reproduce this issue. However, there is a good work that have been done already by Joe Plomin, who tried to correct this effect on spice by a straightforward like tilting of the data in the detector image. So we still have a large PSF, but it is like not oblique like this, but direct. That means this effect would not be produced. Still, the width of the line is dominated by the PSF, unfortunately. So we cannot do any thermal analysis with it.
Okay. To go to the plumes.
Yeah.
What do you had? I don't remember where you had one slide where you were showing the jetlets and the different structure within the plumes.
Yeah. You mean?
I think it was the conclusion of your around the conclusion of your work on the plumes. Yes.
Mm-hmm.
So you have these jetlets or plumelets that you're showing.
Yeah.
If you have a higher resolution instrument, what do you expect to observe in terms of the fractionation of sulfur? in the jetlet, what do you expect to see between the in the plumelet and around in the interplumelet region?
Okay. For sure. First of all, in the plumelet, more of I would think of, not in the plumelet areas, but let's say in the small loops of those areas as they are reconnecting, we are expecting to have more fractionation. However, in the intern areas, we should not have, because they are direct open lines, we should not have any field bias observed in there. And also, since we spoke about the high resolution, if we have also a high temporal observation, we can see that whenever some areas reconnect, or there is a lot of reconnections at a certain area, we should, in principle, expect more sulfur fractionation in one part of the plume than the other one. Of course, because we are not expecting that the plume would be like reconnecting in a homogeneous way everywhere. So we are expecting like to be variating the same way the plume structure variates.
So what is a typical time scale for fractionation? I mean, according to the ponderative force, I mean, if you have one reconnection event, you're launching wave, how long does it take to fractionate the sulfur, and how long does it stays that way?
So for the time scale for the ponderative action to take place is the time scale for the plasma to go from the upper chromosphere to reach the transition region. So I would say in matters of like minutes, as I said before, not minutes, like singular ones, like let's say 20, 30 minutes. And this is like in case we have really like strong ponderative force, because here, as I told you, like we still have to understand its action vis-a-vis the turbulence, vis-a-vis the ion neutral coupling, with the hydrogen ionization levels. But still, it is. In fact, with Delzana, he told me like even like in matters of 10 minutes, of tens of minutes. But at least for me, for the scale, I would say 20, 30 minutes.
Okay. And probably my last set of questions regarding the. I mean, so you've been writing that you're trying to discriminate. Well, I mean, you've been discussing, let's say, discrimination of type of waves, right? I think it's in your conclusion, if you your slide 72, probably.
No, conclusion.
Yeah, I think it's okay. Yeah.
Oh yeah, this one.
Okay. Proxies for chromospheric wave dynamics. I mean, at this point, you're not able to discriminate the different types of waves just with the fractionation. You need a model. You were mentioning torsional waves. Do you know why the torsional waves would go deeper in the chromosphere?
Well, yeah, this is actually one of the questions that I'm afraid of. So, from my understanding of Lemming's model, he have explained that in case we have torsional alpha waves, these kind of waves have less, or they are less damped when they penetrate into the chromosphere with the barrier of the transition region. So, compared to, for instance, shear alpha waves. And with this property, we have more possibility of alpha waves going deeper into the chromosphere. So this is the overall image that I have.
But do you understand why? What makes them different? I mean, why is a torsional or having spherically polarized waves makes them different than longitudinally polarized wave? You're talking about shear waves.
Yeah. I have a problem understanding this. So I have followed the explanations from him, but I had a problem understanding the effect exactly that causes the torsional alpha waves to leak more into the to the chromosphere, unfortunately.
Okay. I won't bother you more with this, and thank you again, and congratulations.
Thank you so much.
Thank you, Etienne. Alessandra, do you want to carry on?
First of all, thank you for your presentation. So I've got two kinds of questions, set of questions. So the first question is related to, you talk about the immediate elements. You said that in the table you put a sulfur and carbon. You then concentrate on sulfur.
Yeah.
Carbon is a little bit higher. It's about that. Yeah. So
as for phosphorus, I think.
Yes. But you just mentioned these two. So, in space, obviously, you have a few carbon lines. You go carbon 3, you go the carbon 2 blended with oxygen 6.
Yeah.
So I know that you have done analysis, but have you done any kind of linear check or something that could sort of lead to the fact that the carbon could behave as sulfur?
Well, for the carbon, I haven't even tried. However, I have seen other people try this. Varisano, for instance, I have seen some plot of hers, but I would not trust too much the carbon 3 because it is a highly opaque line. We will have opacity issues. Maybe I would show you. I think it is around like 20,000 Kelvin for the carbon 3, if I'm not wrong, which is too cold, and it is like within the chromosphere. Basically, we are using nitrogen 3, and nitrogen 3 already is like at the limit, and we have to be careful whenever we go to the active region. So maybe I would show you the video. Yes. So this is from the presentation. So we have Lima beta, we have carbon 3, which is at 20,000 Kelvin, and also even if we measure this, we cannot compare with the corona because at this point the ponderomotive force predicts that the ponderomotive force model predicts the fractionation starts to happen. So it is the top of the chromosphere. So maybe we would not measure sulfur carbon fractionation, but in the corona it is fractionated. At least at 100,000 degrees, we are well above this this layer. Understand what I mean?
Yeah. Just I wonder, if you started to think about that, because the opacity says that it is affected by opacity, but it's not as strong as possible lines like carbon 2.
Oh yeah.
So
we have also before tried to do sulfur over oxygen at the beginning of my thesis, and that after we studied also the oxygen, it is really like weird in terms of opacity, so we do not trust it and we switch to nitrogen.
Okay, that was one of my other questions. That was in in the slide 47. You talk about the fact that in fact what you thought was that the nitrogen 3 and nitrogen 4 compared with sulfur 4 and 5 was the best kind of set.
Yeah, this is the best set that we have. Yeah.
Oh yeah. Okay. In fact, my next question was related to what you just said. There was you said that you didn't try to use the oxygen, or you tried to use the oxygen 4, but what?
It was oxygen 3 and 4.
Yes, 3 is complicated, but the 4 is very close. At least the 787, because the other one is not really reliable. Yeah. But the 787 is formed at very close temperature, sulfur 5, and is very close to sulfur 5.
Yeah, they are close. Yeah.
So have you tried to use that, or?
And I told you it is one of the ones that we have tried in the beginning. Okay, there are two reasons. First of all, we cannot use it alone because the selection of lines have to be carefully done, so there is no temperature sensitivity in it. And we need the oxygen 3, and the oxygen 3 is ugly. And oxygen 4 by itself is still, the oxygen lines are always difficult, even like compared to other elements that's like generate at similar temperatures. So their issue is purely from their type of elements and their atomic composition and the electronic composition. So they are more prone to those opacity issues than, for instance, given nitrogen or sulfur. Yeah.
Okay, so that's the reason why you decided to don't use that.
Yeah. 6, 7, 8. I think it is related to. Please correct. Run after me because run the research after me because it has been a long time since I opened the documentation of Chianti. There is a relation with like lithium-like ions, beryllium-like ions, and oxygen 6, like falls within those kind of elements, and those cause problems with opacity. Yeah.
That's okay. Yeah, my question is just why I wanted to understand why you didn't use. There are lots, you know, from the atomic side, there are lots of problems in that.
Yeah.
So I think that is something that can be still discussed and try to be used safely. But I just asked why, but that's fine. That's fine. The other question is more technical. In the first wind soup, you said that I use. You didn't say that, but in the thesis you said that you used the 4-second lead and the 6-second lead.
Yeah.
Is that correct?
Yeah.
So you analyzed 4
together. Yeah.
Okay. So my question is, when you because so you said so to remind me, you did the fit after you've been or before you've been?
No, after you've been. After I've been.
After I've been. So did you find any difference between the observation that was taken from the 4-second lead and for the 6 in the fitting procedure?
Honestly, I have well in the fitting procedure, in the parameters, like the maps that I have had, like the radiance maps.
Yes.
I had doubts on that at the beginning, and I tried to plot the mean for different ones. I plot them, the error estimation on each one. I plot them, and I haven't seen that much difference. At least if there is something like it needs a lot of analysis. We had also a second, like if I go to, so during this moment, we were observing another coronal hole, and we have used the same set. So it is like alternating between 4 and 6 arc seconds, or sometimes 6 arc seconds are more than that. I found that there is more difference when I switch between 2 areas than I have like between two slit selections. So I think I would be safe to say there is not that much difference.
Thank you. I've got the last couple of questions that are related to the slide 72. That's my final.
Don't worry, you're welcome.
I think that's something that I have to ask, but I'm sure that you got good progress. So I can start. These 2 questions are related to the future improvement and are related to the last section 6.2 of your thesis. I think, from my point of view, are 2 key topics that really are needed to increase the accuracy of the analysis for the spice data. One was the issue of the density, the first one. Yeah, okay. And so on these, I've got 2 questions. One is, so let's concentrate on the fast wind soup. Did you have some spectral atlas? You had the 6 seconds later, 4 seconds later composition map, but did you have also some spectral atlas?
Yes, there are spectral atlases. Yeah.
So the spectral atlas
for the density you are speaking.
Yes, I'm talking about the because you said that the main problem was that the only key ions was the oxygen 5. When you go very complex multiplet, you said it was 9 lines. So and this has been studied in Soutenance as well. So there's a good starting point. And you said that in the data you had, the two composition raster, you didn't really have the full multiplet, so you couldn't derive the density. But you had the supporting spectral atlas in the same set.
So you mean in the plume observations,
for the plume, yes. Let's just concentrate on the plume. So I was wondering why you didn't at least try to give an estimated. I know that is complicated, but you also the summer support that allow you to find a way to fit lines.
Yeah, you are totally right. When we have, like with Luca and Clive Homo preparing this soup for instance, for the plumes, we have plugged in some spectral atlases. However, the issue is that at that time I didn't have the time to do density diagnostics on that. In order to do the density diagnostics with this horror show of lines, we need a lot of careful analysis on the blending, on the PSF issue, and on the absorption. This is oxygen 5. So also there is an issue of possible absorption. So we have to take all of these into consideration. I'm working on that. I'm really interested in publishing like a paper on the spice density diagnostics on this. Because it will open a lot of opportunities for further diagnostics. So you have the opacity. We have to find a way to figure out whenever we have opacity to not to not rely on the density, and also which is even half done during my PhD. With saffron, we have to fit it in an intelligent way to avoid the blending issue. So for now, maybe you read it in my thesis, I have the option for constraints. It is like easier to integrate. I can have constraints on the lines. They have, as you can see, like some of them have the same response. So I can constrain the intensity, their position, and their width. Well, considering that those are good contribution functions, there is no errors on the contribution function. There is atomic physics inside. So yeah, and you see, like there's a lot of work to do. So it has to be a side project to be done. Yeah.
So my very, very last.
You're welcome.
It's related to this point because it's linked to what you just said. Is the opacity problem?
Yeah.
Space is sort of from sphere, transition region, slow corona. So there are lines that are affected by opacity. You said oxygen, partially carbon, and so on. And this is something that you would like to improve in the future. But you already had some idea how to approach this problem, so without going into the full radiative transfer model, which is very complicated.
Yeah, we have thought about it. So I wasn't expecting this question, so I forgot the actual mathematical model that I have used to do that. But Eric have already done, I think, some work on the opacity. So by scanning so I have read their work, and it looks pretty straightforward and easy to do. The only maybe no, not easy, like instead of like really doing full modeling. I'm sorry, I don't want to downgrade your work. What I want to say is that all what you need, you have to have a side-to-side scan of the sun in a given line, and then you try to do the analysis, or maybe the most difficult part is to find the quiet sun areas where there is no activity, and then sum the pixels, and then try to fit that to a given spectral, given like basic model for the emission as function of the length of the atmosphere at that location, or the length of the emission area. And from that, you can have an estimation of how does the opacity affects the results. Yeah. So yeah, it was like a really interesting work, and it would be like the first thing to do without like going a full-fledged modeling with that. Yeah.
Okay, thank you. Thank you very much for everything.
Welcome, and sorry for downgrading your work. I didn't mean that.
Sorry, thank you, Alessandra. David?
Yep. Hi. Okay. Since you said it was easy, let's go into Alexander. No, but that actually relates to one of the things I was going to ask. I mean, all of the work you've done is excellent, and I think this is very good. And you've done a lot of work on understanding all the complexities of all these different things, bringing it all together and understanding how these results relate to space results and how that relates to automotive force model and bringing all the complexity and giving an explanation of everything you've observed. But of course, and that's great, but it's obviously a very, very complex thing with many, many different issues. You've just been talking about opacity.
Yeah.
I feel like when reading the thesis, there's a connection between the uncertainties, what you've done in terms of understanding the uncertainties and the assumptions of what goes into all this analysis. And then when you come to doing the analysis of fractionation and you're getting, for example, for space, but quite small fractionation levels. I just wanted to probe a little bit your understanding of how much the assumptions, the kind of, how to put it, the sort of uncertainties we expect to have are probably larger than what you're describing in terms of your results. I think.
Yeah.
For example, when you're talking about atomic data uncertainties in I think chapter 2, you mentioned like they're accurate to like the data's accurate to like 8% or something like this. And then
wasn't that in the photospheric?
In the photospheric one,
yeah.
But and then you're talking about calibration is 20% and stuff like this.
Yeah.
But things like opacity that you've just been discussing can completely change your intensities by a much larger factor.
Yeah.
And then there are other things that you didn't touch on, like, for example, non-equilibrium ionization. You mentioned just a minute ago about lithium light lines, beryllium light lines.
Yeah.
Those kind of things.
So what you have to do?
Lithium light lines, beryllium light lines. Those kind of effects will completely change your diagnostics. They make them invalid, essentially.
Yeah.
So do you have some kind of, you've obviously looked at this kind of thing, but what is your feeling about that kind of thing? Because later on you talk about 10, 15, 20% levels of fractionation.
Well, for me, I do not give it like a kind of a feeling, but I just work with the state of the knowledge that I have at the moment. So I will try to get as much information on the data and the errors, and then from that try to estimate the errors at the best that I can. And sometimes I even over-exaggerate and elevate the errors to make sure that I am not like falling in any kind of extra stuff that I didn't put into consideration. But still, there is always a possibility of stuff being wrong or the estimation, the field bias would be wrong. This is the nature of science. Maybe I would give an example. Just 10 years ago, like there was like estimations of the field bias of the order of 10 and 20, and right now, as the data is getting better and better, we are more into 3 and 5. So not even like in the beginning of the field bias or the composition work on the corona, you can see like values that like staggeringly high, still they get low. So what I am doing in this study is to work under the conditions that they have. I put all the sources of errors, and then from that I give an estimation. And then if the results are within the errors, we find good thing. If we don't, even if we don't have a result, it's in itself as a result. Now, what are the stuff that could be wrong? First of all, we will start from the estimations that we have. First of all, we have the modeling of the line. So just 2 months ago, I have read an article on the Ci chondrites composition of the sulfur. And in their work, they have said that there is underestimation or overestimation. But in general, their work stipulates that the abundance of the photosphere of sulfur maybe is different. And when I have calculated like what would be the results in my studies, I found that I might have field bias underestimated by 10%. So maybe the sulfur is even higher than what I have like there. So the abundance in the photosphere that we use as a reference is a key that if we change, but it is a really small one. The calculations in the contribution functions for the contribution functions. So I have been to IRIS and a Hinode meeting, and they have announced the new changes to Chianti database, and some lines have just like gotten down or up by 6, by the factor of 6. It is something that evolves as much as we add physics into our atomic calculations. So the contribution function could be changed. What else? The instrumental side. So from what I have, I use a given model of error estimation in my L2 data. So maybe there is another variant that plays in that. Not only fluctuations in the instrumental side, but also biases, which is even more dangerous. But at least from right now, we have a good modeling from at least from what I get from the SPICE team. And what would be else? Yeah, and then the PSF, the contribution of the PSF in on itself. For instance, you know that we are using sulfur lines for the analysis. There is a magnesium line next to it. And those kind of blended lines are difficult to analyze because they can contribute to each other naturally. And with the PSF, they can also have another contribution because the PSF is not only the fact that it's wide, and but only the profile is not exactly a Gaussian. There is small wings in the spectrum. So when you have sulfur and magnesium next to each other, whenever magnesium is intense, its wing also is feeding the sulfur because I am fitting to a Gaussian, and this also could contribute to the errors. But all of those, I tried to make sure that I took them into consideration, and then like propagate all of those errors into the final results. Yeah, and there is maybe and of course from those you can have a biases that are like from the fact that you inject into the LCR method, into the optimization of alpha I and beta I because they depend on the contribution function in the EM. So all of that goes into the final estimation of uncertainties. However, I tried I got all what I have like under like the light and try to use them all to estimate errors. And if in the future we find out that there is another source of errors, well, I will republish a paper debunking myself. So.
Okay.
Yeah.
Yeah, you mentioned the LCR method. That's interesting to me. I get a little bit confused about what you were doing with that when it comes to the ice.
The LCR method and what?
The ice data.
Yeah. The ice data.
Yeah. You talk about iron plus silicon over sulfur.
Mm-hmm.
I guess that means that you're using the linear combination of the iron lines.
Yeah.
With silicon over sulfur.
Yeah.
I got a bit confused in the thesis as you were referring to previous work by me and others, and talking about iron and silicon fractionation compared to sulfur.
I was referring to a work of yours.
Well, yeah, I'm just wondering whether you checked this against like the full DEM inversion, because what we have done with ice before would be to take iron lines to understand the shape of the DEM, and then alter the magnitude to match silicon, and then compare it with sulfur. So it would still be a silicon-sulfur ratio alone.
Yeah. But
temperature and density dependence is taken away by the iron, and I guess that doesn't happen here because you're matching.
Would you re-explain again? I think I haven't got quite the idea.
Okay, so for the way we do it or have done it is we want to measure the silicon-sulfur ratio.
Yeah.
But there's a temperature dependence.
Mm-hmm.
And we don't have enough silicon lines.
Using LCR or DM inversion?
The DM inversion.
Oh, yeah.
Okay. And we don't have enough lines. We don't have enough silicon lines to understand the DM. So we use iron. Mm-hmm. But iron and silicon are supposed to fractionate the same way, but they don't necessarily. Yeah. So we have to scale them.
Okay. So how do you know about the scaling factor? Actually, I'm quite interested.
Okay. Well, I mean, you scale it, and that would give you a number. And if it's within the calibration, then that's okay. But if it's something big, then you might have a problem.
Okay. And this fractionation difference is linked to it is like an intensity, like instrumental effect from iron and silicon differently, or the actual composition is different?
Well, this is a question. In theory, we would say it's an instrumental effect. But as you're discussing, self-refractionates differently in the chromosphere and the coronal. So is there a difference between silicon and iron? We don't know.
Okay, yeah.
But we assume that the difference within the calibration area is okay.
It is quite interesting what you have said, because there is this stems this like maybe pose another idea, if you don't mind, in the same point, is on the fact that the ponderomotive is a model but not the model. So it is one of them, but still, for instance, in situ measurements, I can see some gravitational settlings. Some scientists speak about research, or publishing authors speak about gravitational settling, and maybe between silicon and the iron, like there is more to the ponderomotive force effects. And also, I have been speaking also with Nicolas Poirier, who is a supporter of another type of model, which is the fusion model. And like maybe because what we are measuring is not the Fib bias, we are measuring the ratio. So if there is a gravitational settling or diffusion effects, it will be indicated or included in the data. And maybe it is like from me, I would think that the ponderomotive force with a variation of between 7.9 and 8.15 would not have a great deal into iron and silicon like as variation. But if there is like something other than that, like gravitational settling, diffusion, or this kind of stuff. But I haven't looked in details on how those effects exactly work, but I know that in the data, you can still see some effects of that. So I believe that maybe there is a interplay of multiple effects in that. And at the end, it goes back to your maybe remark on the fact that iron and silicon are supposed in the ponderomotive force to have like little to no difference, but still we are maybe going to find something.
Yeah, I mean, we do see some evidence of a variation in fractionation as a function of Fib. So if you go to the very low Fib elements like potassium, calcium, you see a difference.
Yeah.
And so I was wondering, actually getting back to the question, there's two things. First of all, did you check your method against that type of ice analysis? And also, did you notice anything unusual in the sort of the alpha and beta coefficients you're getting, or that would indicate anything like that?
For ice, the work have already been done. I think the previous PhD before me have done this work and already published it. And from what I see, and also there is, was it with ice or with spice? I think with ice. There is a boundary, coronal hole boundary paper, composition paper. And in their analysis, I think they reported that the LCR slightly underestimates the fractionation compared to ice. So yeah, you may have methodological differences between them, like due to the nature of the techniques.
Yeah, I think the DEM inversion, it also depends on the method you use for that. Because, for example, if you use an iron lens and one silicon line, people here will know there's been a long years arguments about one extreme of the DEM where you smooth it, and then other extreme where you make it mathematical to catch all the intensities, reproduce everything. So you get.
So it would be like fluctuating.
So you could have it like put in all the lines, all the spectral lines you have, and try and match all of them, and you get a very complicated DEM distribution. Or just say, look, I know that these ones at these temperatures are reliable, so it's very smooth. And when it comes to something like the bias measurement, that makes a big difference, because either you're taking one point and saying, I'm going to match that, and I get a magnitude of 3, let's say, Or you've got 4 or 5 points and it's going like this, and you're getting some kind of average. And so I'm wondering what side of the spectrum your method is falling on. And if you're saying
for silicon and iron in ice.
If you're saying that previous analysis showed that it's slightly lower, then I guess it's falling towards the averaging side. So that was my question, but you've already answered it.
No. I haven't tried to exactly try to find like the difference between silicon and iron in the ice observations. But, well, maybe it will be another project for another for another time.
In that technique, you said you use reference EMs. Are these taken from
for the LCR? Yeah, they are PNT the EMs. However, you would say, how do you know? Because Natalia have already, Sabrina Prado, the person who have developed the technique, have already done the comparative work using multiple DEMs, and the results were close to what we have with ice, and even the variation afterward. If you take different DEMs, you have a really small variations in the Fib bias. So the coefficients by themselves do not change a lot, and the Fib bias estimation at the end is not that hard. However, this is conditioned by the fact that you have really close contribution fractions. So if they are so far away, like you cannot take neon with oxygen, like at really like high, large differences. So the closest the profile you have, the perfect you have your bias without the EM sensitivity and temperature sensitivity.
Okay, one other question was on you sort of emphasized the importance of subplots.
Yeah.
And yet in the plume example, the fractionation levels you get are very small.
Sorry?
In the example of the plumes,
the
fractionation levels you get are very small.
Yeah.
So that's a case where since sulfur is fractionating less than other elements, it might be better to look at something like iron or oxygen, which I guess you don't have, or spice.
No.
But I wondered if you sort of, you didn't really answer in advance, but you've ended up with a situation where the diagnostic you use is very marginal. On the other hand, as you pointed out, sulfur is a great diagnostic for other situations. And one of the situations you mentioned at the beginning, but you didn't mention again, was in energetic particles.
Yeah.
And I wondered if you thought anything about that, because the Fipt bias that you observe in sulfur, because it's the mid-Fipt element, is much higher in solar energetic particles than it is in, for example, the solar wind.
Mm-hmm. So is it higher? I thought it was not that much.
The ratio with like the high Fipt element.
Oh, so I mean the solar energetic particles have a higher composition of sulfur compared to slow solar wind.
If you take a ratio to nitrogen, like you're doing in space.
Yeah, but
if you look at your data points, the red ones have a tendency to be higher than the blue ones.
Yeah, this is in the low Fipt.
Yeah, so in this case,
you have difference. Then in the solar energetic particles, you have like low Fipt bias, and then in the slow solar wind, you have.
I think it's the right thing. I'm thinking the wrong thing. Looking over sulfur, I'm thinking.
Yeah.
So well, that's interesting. Okay, so it's the other way around for space because you're using sulfur as the low Fipt element.
Oh yeah, I use it as a low Fipt element. Yeah. This is why I have warned for when used for ice, when we interpret the data, we have to think of sulfur also because it can fraction. Well, in general, for instance, it is your work. I am speaking to the author of this work. So in this, I showed it in the introduction. So this is Brooks et al. 2015. Here there is like a full composition mosaic of ice using silicon over sulfur, and here I would be like would not be worried about sulfur at all because we are doing a generic analysis. But whenever we go down to the plumes, we have to make sure that like plume food points, etc., we have to make sure that it is not expected for software to fractionate if we want to directly measure the silicon iron phase bias. If we want only the ratio, well, yeah, the ratio is the ratio. Yeah.
So it's the opposite of what I was saying. In that case, it's still a diagnostic for the reverse. For the spice data, regions with the sulfur nitrogen ratio is lower than that.
Than 1.
Yeah, inverse flip.
Inverse flip. Okay. I haven't looked thoroughly into the inverse flip.
Probably ignored that because we don't believe inverse flip effect much.
No,
I mean in general.
No, it's not that I don't.
No, I'm not saying
believe.
saying.
Okay, yeah. No, because it is not the kind of. There is a difference in terms of physics for this element, and I don't know exactly how it would behave in these kind of cases. And another thing is that we need to have energetic events, flares, and this stuff to study using composition. But I don't think that we have a lot of composition studies during in the midst of a given flare of an energetic event enough to create like a hot evaporations that create that inverse flip effect. So I didn't go into it. My interest was on the on-flip effect, and I barely managed to do it. Yeah, it was like, but still, it is an interesting aspect to look into it for the inverse flip part of this.
It might be interesting to link it with jets.
Well, the jets also show the inverse flip signatures.
No. Maybe in the sulfur nitrogen.
Okay, yeah. For the jets also, it will be a great thing to do because they are open for the into the solar wind.
Okay. One last thing was actually you mentioned on the models of the competing model. You emphasized Martin Lamming's model a lot.
Mm-hmm.
But in the case of the plumes, you know Juan Martinez?
Sorry?
Juan Martinez, the color.
I think Martinez is ringing a bell. I think I have read something about him. But
he does an MHD simulation, also including like quantum force.
I think I have read some articles from him.
You might be interested in his work. Essentially, the prediction is the opposite of Lamming, the direction of the quantum is opposite. So in the case of the plume, it would be the direction of the plume. The fractionation. Direction of the
he says that the fractionation is in the direction of the flow.
In the direction flow of the contributive force. So rolling up and down and low and high pip and everything. In Martin's model, the wave direction is opposite to the contributive force, but in Planck's model, they're the same direction. So if you have waves propagating along the plume, some people have seen in X-ray data.
Okay. Correct me if I'm wrong, but this is in the case where you have longer periods, like the low frequencies of alpha waves, where you will start to have directionality, I think. Because from what I have read, it must, so in case of high frequency, which is something that we should not have that much in the chromosphere because of the cutoff that will be absorbed. Those high frequencies will be absorbed due to the plasma frequency. You will have no directionality. It is only dependent on the inverse of the gradient of density itself. But the ones that we have a lot of them, which is the low frequencies, they are dependent on the direction. And I think there is a paper published in 2025 speaking about this kind of 24 or 25, speaking about this effect, where they found that in the case of, for instance, wave conversion, where you have alpha waves that are generated from the bottom, the frequency will not be that high, and it will not explain or it will not contribute to the fractionation that much. And this is why in the conclusion of my plumes part, I said that the fast and slow modes in the top of the chromosphere have been argued lately that they should not be that much influencing. But in the case of high frequencies, it should be like in the direction, in the inverse direction of the gradient density. Or I might be wrong. There is always a chance of that. Or maybe in the plumes, if there is those fractionations, it would be something of the coronal. Although I am skeptical of that.
Well, my point was mainly that if you're aware of it, because there's a clear difference in prediction there, and you're analyzing relevant data to that.
Yeah. Well, first of all, I would like to read this paper.
Yeah.
If you have it. Yeah. And second of all, if there is such an event, I am not aware of. In any way, if even you mean that this would create an inverse, like the sulfur would be less fractionated, or it would be fractionated just normal, but.
I'm not quite sure the exact prediction of the model.
Yeah.
I was kind of asking again. But...
Okay. Well, I haven't passed by this, and if it does create fractionation, I would not see the difference because both of the cases fractionate. If it creates inverse fractionation, I would not be able to see it because I am considering high density estimation. So I have values below 1, but I don't know whether it is this inversion or it is the density effect. Yeah, so I would like to read this work.
Okay, I think that's all.
Thank you so much.
Thank you, David. Well, I guess it's me now. And so, Slimane, I want to congratulate you for the manuscript, which was very complete, I found, although I'm not from the field, and very clear, and also for the presentation, which I found very complementary to your manuscript. So, as an outlier to the science, I'll have only naive questions. I was just wondering, still back on your slide 72. You have the saturation curve along the electron density for a couple of lines of oxygen 5.
72.
Yes, that's that one. So I'm talking of the curve as a function of the electron density. So there, the regime of emission goes from n squared to n only on at the high density limit, because you have the action of collisional de-excitation. And so I was wondering, so density is a very important parameter for as you explained, for your modeling of the emission you follow. And so is the plan to use such elements as O5 or that sort of thing, which have the transition in the range of densities which you think are relevant for the part you're studying? So do you want to accumulate data for such species in order to be able to constrain the evolution of the density as a function of height above the chromosphere, or is it something else that you might use to constrain the density?
Well, what I am doing is not, unless if I understood you wrong, I am not trying to get the density as function of the height. I am trying to get the kind of the mean density along the line of sight. Why I say this? Because the lines that I am using are confined to a given height. So for spice, for instance, we use lines that are around 100,000 degrees. And what we do, we try to find the density or the average densities at these layers by taking the ratio of lines. So there is no, here what we are showing, maybe I was showing so here what we are showing are the contribution functions and the ratio between those lines as function of the temperature and as function of electron density.
Mm-hmm.
Yeah, so unless what we are looking for is a line that is temperature insensitive in the same time, it is density sensitive. And this would have a direct consequence on the fact that we can take the ratio observationally between two intensity values and then just extrapolate them and find the density, the electron density.
Mm-hmm.
So this is, but we do not find the density as function of height. Well, first of all, because it is too much complicated, and the second of all, we do not need that much precision. We just need the density at the given height that we are using to get the Fib bias. Have I answered the question?
Yes, I think so. And so you get the material from the lines so you may find the lines which are at the right density range.
Yeah.
For transition from low to high ratio, for instance, as we see here.
Yeah.
To match your density to be determined. So
exactly. And whenever we have the density, it's pretty much way easier because right now our method that is density dependent, we can pinpoint to each pixel of the map what is its density, and then we find the Fib bias. And the errors that are due to density uncertainties will pretty much be reduced. Not gone, but reduced, because, for instance, for oxygen 5, we have this calibration curve, but there is still some temperature dependence. So the curves between the highest and the lowest temperatures are the errors that we are going to use to have our density estimation.
Mm-hmm. Okay. The other thing I was wondering is about the ponderomotive modeling.
Yeah.
So you've got the process that you explained, and in general processes, what you're after, in fact, I guess, are physical conditions at the bottom of these flares. And so I understand magnetic field, magnetic energy density is one of the important ingredients in this modeling. But which are the other important ingredients?
Oh, so it's not the maybe I don't know whether it is a I have explained it bad, but it is the energy density of alpha waves, not the magnetic field, the gradient. So generally, but for this, you only need an environment where there is this kind of characteristic in a given density or gradient pressure, the gradient of pressure. That means the plasma is already evaporating, which is something that is happening almost everywhere in everywhere in the sun. And we have to have the right temperatures, or at least in order to be like a successful model, the temperatures where the fractionation happens must correspond, or the areas where the fractionation happens must correspond to locations where the ionization fraction, which is the ratio between ions and neutrals, of the low Fib element is higher than that of the high Fib elements. Because this force is electromagnetic, it does not affect neutrals, but only ions. So this is the third condition. And also, we don't have to have like a high, mixing in the plasma, whether it is turbulence, whether it is the neutrals, or maybe hydrogen when it is neutral or highly neutral, will cause the ions to be coupled to those neutrals. And the consequence is that the ponderomotive force will not act. So we have to not be too much down in the chromosphere to have too much neutrals, and not too much up in the corona where all the elements are ionized. Thus, there is no fractionation. So there is no ponderomotive force at all. Yeah. So this is basically the main conditions for this force to act.
Okay, thank you. And last questions, open one. So you've been talking about composition. So it's a touchy subject in astrophysics, of course. Do you think that this Fib effect might blur the cosmic abundances that one can derive from observations, or is it only any effects?
You see, the composition may what? Sorry.
So the composition, the cosmic abundances in the sun, for instance, are mostly determined, I understand, from the chromosphere, so the emitting region. And so now you've got, you're moving out of this chromosphere some elements. Is it a very small effect, or is it something that one could see in the determination of elements, I don't know, sulfur, for instance, or from the sun's surface?
Oh, sorry, just to repeat the question if I'm not wrong. So you asked since
whether this moving of elements is something really important at the scale of the sun's surface, or whether it's only a tiny, I mean, in fact, what's the fraction in percent of the sulfur displaced from the sun's surface due to this FIP effect? Is it, I don't know, 1%?
Oh, so to answer this question, I just remind that this effect is not like homogeneous everywhere. So it appears, it depends on the location, and also it depends on the time. So for instance, whenever we are in a quiet sun, we have less fractionation. So whenever we are at the down cycle, we look, or the lowest activity of the sun, if we look into the measurements of the wind, or the remote sensing observations of the FIP bias, we are not expecting to have any much fractionation. However, when we are in the active parts, in the active region, maybe more importantly, we see this fractionation takes place. And so, as I told you, it is not the same. And about the how much it does play a role, I don't know if anyone have done a bilan, like a study to have the entire sun composition evolution with time. But I would expect it just varies depending on the solar activity. Does that answer your question?
Yeah,
or okay.
It was a difficult question. Thank you, Slimane. So
Okay.
time now to leave the word to the advisors.
All right, okay. So no, I do not have questions. I guess I've seen your presentations quite a few times, but it's generally the routine to give a few words on these past 3 years and a half, even more, of your work. And when I think about the work that you've done, I think there are two things that come to mind more, but the two main things are first, your work ethics, and the second one is your enthusiasm. And I think one fits the other in a very, very interesting loop. The first one is enthusiasm. So when you reached out to us, when we proposed an internship, I think what really struck me is how enthusiastic you were working on any subject, but also you really put in the effort to really acquire very quickly the skills. I don't know whether people could really tell, but the first work that you did was on this eruption. And very quickly you managed to work on SPICE, but also on the other instruments in solar orbiter, and then you extended that to other spacecraft as well. And that was really, really fast. And in terms of developing saffron, again, I think the jury could tell, but I don't know whether people in the audience could tell as well. But you've put an enormous amount of work for something that didn't exist. So we didn't have the tool at the beginning to have all these diagnostics with SPICE, and you really put your heart into it. And I was really, well, it was a big effort.
Thank you so much.
So I think I can thank you for the work that you've done, but also for the work that you've done for SPICE in the community at large. And I know that your code is going to be open, or it is already open source. And so hopefully more people will use that as well. For your work ethics, sometimes it drove you to work really hard and maybe too much. But I think you also learned during your thesis to balance it with doing some other things. I know that you have some climbing partners in the room. And I remember that we also spent hours, even late at ISTEC, working on your paper. So I've seen you working really hard, and I think that's a really good skill to have, and you're really focused as well. And then there are other things. I've seen you change. I've seen you mature. At the beginning, you didn't know much about spectroscopy, and to be fair, I didn't know either. And in the end, I'm learning so much from your work. You're the one who is teaching me all of these things. I've learned so much about FIP that, well, I didn't know much about it to start with, but I feel that it's really been great to have my horizons expand through your work as well. And also want to say that I was looking at what we have done. So of course, we've done a lot of work, whether it's on eruption, the active region, plumes, and more active regions to come up. We participated in the spice planning, the SOUP, so the solar video plans. But we've done other things. We've seen a total solar eclipse. We've traveled to Texas. We've seen a basketball game. We did a stand-up paddling with Anna in Leiden. So he came quite a few times. And what I want to show is really that it was a pleasure not only to work with you, but also to spend time outside of work with you. So it's been a pleasure to know you. And I do hope that we continue to work together and that I continue to learn.
Pleasure is mine. Thank you.
Thank you.
So we met more than 3 years ago when I was teaching UV spectroscopy, the master's plasma physics, and so that's how you asked us to do your PhD with us. And so then you revealed yourself, I think, as a virtuoso of Python and data analysis. You worked really hard for that and put your heart at it. So there's a lot of hidden work that maybe cannot be seen by the public, but for example, just a simple light curve, that, like from those from a EY FSI, it looks trivial to obtain, but already you had to correct some flat fielding effect due to the off pointings and so on. And of course, then SPICE and UV spectroscopy in general, but SPICE in particular is not the easiest instrument to work with. So it was really a lot of hidden work on using this data and data analysis. And so during these 3 years, so I think we were all three of us are very complementary and really worked well as a team. And you always happy and enthusiastic. So of course there still was some challenges with the French administration or with the paper publications process, but you really made also huge progress in all aspects. And so we'll see what the jury decides for the PhD. So much.
Okay, thank you to the advisors and thank you to Slimane to extend this long question session. And so I guess now it's time for us to go in the other room and debate. So see you in a moment.
Thank you.
Do you hear some zoom? Yes. Can you hear us? We're just checking. We're just going to check the picture. It will be okay. Il est où Alfred? Noah, il est parti le chercher. Noah est parti le chercher. Ah, okay. Just waiting for someone. For our technical expert.
Un, deux, trois. C'est que les
Normalement, ça marche, c'est juste égal.
C'est bon pour le son?
Je pense que c'est bon. Oui,
Ouais.
C'est bon pour le temps, Alfred?
cool. Donc Laurent, tu peux.
J'y vais. Okay. Yes. So I'll do this in English, because that's the feedback from the juror. So Slimane, the juror has discussed at length, and so we are very pleased to announce you that we award you the title of Doctor in Astronomy and Astrophysics of the University of Paris-Saclay. So that's done. The suspense is gone. And for the following reasons, we found we've been very impressed, in fact, by your command of your field and of the methods that you've followed to study this field, to push this field forward. Basically, I mentioned data analysis and also scientific interpretation of your results, both in imaging and also in spectroscopy. So all this involves different tools, different set of minds, theory to be able to get the essence of the models, and also data, signal to noise analysis, and so on, to be able to compare the data to the theoretical models. So you've been able to manage all this. And you answer to the questions amply demonstrated your command of all these different aspects, both very pragmatic or also theoretical. And so all this was done in a very enthusiastic, at least in the presentation, that was quite obvious, and also in your answers to the questions in a very enthusiastic manner, and with rigor and also systematic discussion of the different aspects involved in your science. So for all this, we congratulate you. We said also that having this command of your field, and you were able to get this hindsight that pushes you to new perspectives important for you and your community. And we encourage you to publish all this stuff. We know it's already started, and we motivate you to go beyond and get this first paper published. The second one is in good shape, I understood. And we also encourage you to pursue on your research track. So the other aspect of this part of the defense, which I don't think is really necessary, because all of what you've done, your manuscript, your defense for the part we've seen, but also all what you've done with your advisors, amply demonstrates that you've got an ethics of science and that don't really need an oath to be sworn to say that. But okay, if you want to swear this oath, you can do it now. And so maybe I'll leave the word to you to do that.
Thank you so much. So, in the presence of my peers, with the completion of my doctorate in physics, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. Thank you.
Thank you, Slimane.
Do you want to say final words or?
Yes. On my side, it's finished, so the word is to Slimane.
Well, thank you so much. Congratulations, Slimane. Thank you all for coming. I don't know if you want to say a few words or you're done.
Acknowledgement part. Okay. So, just I put out something. No, I didn't. So, thank you so much, everyone, for coming. Thanks you all also for my jury for taking your time that I think that is precious for you, and that means it is precious for me that you gave me that time to read and analyze my work. And thanks a lot for your interest, and thanks for the exchanges that we have had right now. I have learned and grown more from them, and they gave me also more like aspects about the way to go forward. And also, Laurent, I hope you will recover soon. I will see you in person. Now, also, I would extend my thanks to my supervisors. Though in those 3 years, I have made not only a friendship, but a long-lasting friendship with some of the most brilliant people I have met, and they have had a huge honor to be their students and to nag them about my problems again and again in Slack in 11 p.m. and somehow 5 minutes later they still respond. So I appreciate a lot their involvement and their support, and also something that I liked a lot during this work, and it was thanks to you, is that they didn't just push me into a corner with my code and my papers. They have showed me a lot of opportunities, and this is one of the most interesting stuff in my PhD, is that I have done some tasks in terms of planning observations, in terms of contributing and exchanging with some interesting people that a PhD student would never have thought about in his research life rather than his PhD life. So thank you a lot. I appreciate a lot what you have done during those 3 years. And it is also my milestone for a whole decade of university life. So a third of my life I spent it in the university. And for that, the list for people I would thank, and the people for which, thanks to them, I am standing right here sharing with you those beautiful moments are a lot. However, I will keep it brief. Thank you all, everyone, for coming. Thanks to my friends who have followed my presentation and the ones that have followed in online. And thank you for those who didn't come, because most of my friends are in Algeria and it's already difficult to come here. So you are in my heart. And especially for also my team who next to them, I didn't only grow as a scientist, but also grow as a human. I learned how to live the life, how to have good friends, and learned how to rock climb in an aesthetic way, as they say. I learned how to dance Sri Lankan. This is a great thing. And thanks for my technical support, Alfred. You have been here. And thanks to him and me, generally around the lunch table, we are forbidden to sit together because we will speak about Python the entire time. Well, not the entire time. The other part would be about C++. So I thank you a lot, my team, for this opportunity. And also would thank the people who came with me for me today. Unfortunately, the family was not here, but my uncle is the delegate for the mall. And also thanks for my friends from my hometown who came here, I honored them by putting on the dress, or the traditional dress for us. Also, I would thank my roommates and Sylvie, she's not here, who helped me to prepare the food. And she is my landlord, but in fact, she is my second mother. She is like the nicest person. Unfortunately, she's not here. She helped me a lot during those years. And I will end up with the most precious people around me, which is my family, who stand a lot with me. I appreciate a lot their help. They have been really great people. And whenever I have passed by like hard moments, they have been always with me. And I would end up thanking the most precious of them all, which is my mother and my father. You all, يعطيك الصحة يما. Thanks. Remember this, I will not cry again, so.
You're precious.
Thank you. Sorry? Oh, yeah, yeah, and please, so please stay here if you want to taste the Maghrebian food and pastries. So maybe for some of them would be something of usual, but for some of them it would be something of new. And this is the least I can do for you, the people who came to support me. Thanks.